So here we are at the step 3 of problem solving, which is basically implementing the chosen solution. So we're going to do those in-out steps in detail now. And normally for other problems, again, we go through some detailed steps. Here we may not have things as complex. So starting with the schematic that we had, this is the schematic that we had, and starting with that, we are going to calculate each one of these terms and then put in this equation. Now for this calculation process, the detailed step-by-step solution is provided at the end of chapter 1. So please look through these steps that will give you in words and in text the details of how you would approach. But here, let's just use these steps. So we're now in step 3, and we're going to just do that. Okay, so the first term we want to calculate is energy in. So the amount of energy that you already know, how amount of energy in a mass is mCp T minus T ref. Now, in a flowing mass, sorry, this system doesn't allow me to write very nicely. My handwriting is better than this. So m dot is the mass flow rate times specific heat times T minus T refer. So let's see how we calculate this. So mass flow rate is density times the volumetric flow rate in meter cube per second. So you can see if this meter cube cancels and we get kilograms per second. Times specific heat, joules per kilogram per degrees Kelvin, and this T times the T in minus T reference. So the T reference, we have taken it to be 0 conveniently. There is no reason that this should affect our calculation. So all of these together is in joules per second. And so multiplied by delta T in second gives me joules. Okay, so now we are in the out term in the exact same way. Volume flow rate times density times specific heat times T minus 0 as the reference temperature times delta T is the energy out. So next we look at energy generation. Energy generation is equal to how many persons are there, so number of persons, and then this one is how watts per person. So these two cancel, so we get watts, that's joules per second, multiplied by delta T is in second. So again, this is in joules. Okay, so the last term is change in storage. What is the meaning of that? Because of energy going in, coming out, plus generation, we're going to have a net change in the energy stored. And so the net change in energy stored is mass M times specific heat times change in temperature over that time delta T. So this is change over delta T. And um, so let's look at what numbers we put in. So mass of air is volume. These are the different dimensions. Volume of the room times density times specific heat. And if you look at the units, the volume cancels out, the mass cancels out here, the degree centigrade cancels out, so we get joules as the change in. So now we are ready to put everything together. These are the four terms that we calculated. We now substitute in the conservation equation. My conservation equation meaning the in minus out. So this is my in, and likewise this is out. This is the generation, and this is the change in storage. So over time delta T, this much came in, this much left, and this much got generated. That led to a change of temperature or change in energy storage given by this term. Okay, so now we have the complete equation. We're now getting ready to solve the equation, but before that, we need to get it back to a differential equation. This is over a small time period, delta T, that we have the change in temperature of delta T. So if I simplify algebraically, I get this term del T is equal to this. Now we make del T go to 0. That will give me the differential equation that we see here. So dt over dt equal to this is my final equation. To solve this one, we need initial condition, because you see it's a first order in time. So when you integrate, you'll get a constant of integration that we need to evaluate. So the temperature at time t equal to 0, we assume for now Ti. This really needs to be given. By assume, we mean that let temperature, let me call that temperature Ti. Of course, we need that. Without that, we cannot solve anything. Substituting into the above equation, we get this one, and so now this has to be integrated between Ti and T. By the way, it looks more compact because that big expression I have substituted for the big expression A. Continuing on solving the equation, okay, so we get, when we integrate, we get natural log, and so that will give me temperature as varying as exponential. So if I substitute for the A now, we get the final solution that looks like this. Note that temperature is varying exponentially with time. Okay, further continuing on the solution process, we can now plug in all these values. So like density of air is given, the volume of room is given, specific heat at 25 degrees centigrade is given. And so all of these quantities can now be calculated. Okay, and so all of these will just plug back into this expression to get a nice compact final result. So my final result looks like this. T minus 41.22 is equal to this. So you can see temperature is varying exponentially. Again, And so if I plot that, it's going to look something like this. It starts at the initial temperature 25, and you can see at infinite time, if you put t goes to infinity, then this term will go away because it will go to 0. So t will become 41.22. So that is my steady state temperature. So this is my steady state temperature. So at the end of the lecture, then we would reach a temperature of 41.22.